Hey there, chemists. In this crash course, we're going to talk about electrochemistry and the things that you might see on the AP exam. Electrochemistry refers to how we use chemical reactions to create electricity and vice versa, how we use electricity to drive chemical reactions. The first thing to review is the spontaneous reactions that are seen in what are called galvanic cells. These are also called Voltaic cells. And they refer to using favorable reactions, thermodynamically favorable reactions, to get electricity. That's the point. That means that the change in Gibbs free energy for these processes are negative, the equilibrium constant is big, and the new property in this unit, the electrochemical potential, is positive. So what does a voltaic cell look like? You've seen them many times if you've done any electrochemistry things. They're usually drawn as two separate containers, usually of some aqueous ions. We'll just use a really simple one of, let's say, aqueous zinc ion in the presence of copper ion on the other cell. Those are solutions. And then there's like a metal bar of the same metal, often sitting in its own solution, or possibly an inert electrode if the electrochemical reaction is not involving a metal. But let's pretend it does for this case. So we could have zinc in a zinc solution, and we could have copper in a copper solution. And then they're connected with a wire, and then something else that's porous or connecting to allow ion migration. They're usually drawn as a salt bridge. I'm going to draw it as a porous container that connects the cells to each other and allows for ion migration. So what's happening in these half cells is we've separated the oxidation from the reduction, and we've forced electrons to travel through a wire. And then there's some terminology that goes with this. The oxidation that will occur in this case is zinc will get oxidized to zinc ion and lose 2 electrons. And on the other side, the copper will get reduced. Copper ion gets reduced to copper metal. The side where the oxidation occurs is called the anode. The side where the reduction occurs is called the cathode. And electrons are produced at the anode, therefore they travel through the wire from the anode into the cathode. And we can look up in standard reduction tables what the magnitude, what the potential for these half reactions is. This is called the standard reduction potential. These are reference values based on 1 molar solutions. And if I look up the potential for zinc, they're always listed as reductions, but you just change the sign and you get the oxidation. So if you look up the zinc value, it's about 0.76 volts. And if you look up the copper value, it's 0.34 volts. That's given straight from the table. They're all listed as reductions, and if you have to reverse them to make it an oxidation, you simply reverse the sign. How do we get the potential of the cell? The potential of the cell is simply the sum of those two. Once you've flipped one to make it an oxidation, you just add them. You don't even have to multiply them by any coefficient, even if the half reaction gets multiplied to balance the electrons. It doesn't get multiplied by some factor. When you add those two numbers, you get a positive 1.10 volts for this very simple example of a electrochemical potential from a spontaneous reaction. The other type of cell is called an electrolytic cell. Electrolytic. These have non-favorable reactions, meaning non-thermodynamically favorable, And we get them to occur by putting electricity into it. So we drive a spontaneous reaction, a non-spontaneous reaction, by giving it electricity. That means delta G for these reactions is positive, K in the direction written is small, and the electrochemical potential is negative. We force them to occur by giving them an electric power source. They're usually drawn schematically as one container, probably with some aqueous mixture of something. Let's say we have aqueous Ki, and then we shove an electric current in it by literally connecting electrodes from a battery and dipping them right into solution. So we have some external battery connected to it, and that battery is essentially what a galvanic cell is. We're using a galvanic cell to create an electrolytic cell, so they abbreviate that entire galvanic cell with a battery. There's notations, positive and negative, for the electrodes. You don't need to know what those mean for the purposes of the AP test anymore. The negative electrode in a galvanic cell is where the electrons come from, and then the positive is where they force electrons to go into, but then that connects to the opposite electrode in an electrolytic cell, so it gets a little confusing, so they don't even require designating those notations anymore. This one's an interesting example because we have aqueous Ki. So in addition to the possibility of potassium ion being reduced to potassium metal, and also iodide ion being oxidized to iodine, these are just the abbreviated half reactions, I'm not even balancing them, we have competitions because we are in water. So there's also the possibility of water getting reduced and water getting oxidized. This doesn't happen if you're not in water. If you just have molten Ki, that's how you make elemental potassium and elemental iodine. But once it becomes aqueous, we have to consider the half reactions involving water. Water gets reduced to make hydrogen, and water can potentially get oxidized to make iodine. To make oxygen. Then you look up the numerical values for each reduction and for each oxidation, and you pick the ones that are less negative. It should come as no surprise that the less negative value for the reduction is the reduction of water. The reduction of potassium to make potassium ion is very negative. The reverse of that process is much easier to do. That should come as no surprise because potassium ion is very stable. Potassium metal is very unreactive. It's probably not clear what's more favorable for iodine versus water. Turns out that it's easier to oxidize iodide than it is to oxidize water. You want the less negative overall E value. That's what you do when you compare these things. So we're saying more positive. So we know that in this case we would get iodine at the anode, which is the name of the oxidation site, and hydrogen at the cathode, which is the name of the reduction site. There's one other thing that you'll often have to do with electrolytic cells, and that's to just simply know what current is. Current is usually given the symbol I, and it's defined as the charge per time. You know this if you know what an amp is. An amp is a coulomb per second, and they use this equation a lot, but it's really just the definition of the units of an amp. It's not that useful of an equation. It just reminds you of what the units are. So if I was given some amount of time, let's say 3,600 seconds, and I told you that I ran a cell like this with 1 amp, I would say there's 1 coulomb per second, and then I can convert my coulombs into amounts of material by using Faraday's constant. There's 1 mole of electron for every 96,485 coulombs. And if I wanted to know, let's say, just how much hydrogen I'm making, I can convert my moles of electrons into moles of H2. Thinking about what the complete hydrogen reduction reaction looks like, there would be 2 electrons on the reduction side in order to make hydrogen gas. This is an unbalanced reaction, but if I balanced it, you would have 2 moles of electrons in that reduction. So there's 2 moles of electrons, 2 moles of electrons for every 1 mole of hydrogen. So we could convert time and current into an amount of substance, for whether it's moles or grams or liters or what have you, all by the virtue of knowing what current is and Faraday's constant. There's a couple of features that are unique to both voltaic and electrolytic cells that I'll just put in between. Number 1, the anode is always the site of oxidation. The cathode is always the site of reduction. That's true no matter what cell you're talking about. And quantitatively, we can calculate delta G from the electrochemical potential. It's based on the moles of electrons in the balanced reaction, that constant, Faraday's constant, and the electrochemical potential. That's true if it's non-standard or if it's standard with that superscript 0, meaning 1 molar and 1 atm. There's another equation that relates electrochemical potential when it's non-standard. It's called the Nernst Equation. E is E standard minus RT over NF natural log of the reaction quotient. Remember, R is 8.314 joule per mole Kelvin, and Faraday's constant is 96485 coulombs per mole of electron. And even though those things are on your reference table, it's certainly faster to just know them so you don't have to keep looking them up as you're solving questions. Okay, that's a lengthy rundown of the kinds of things that are fair game on the AP related to electrochemistry. Let's look at a couple of sample questions. Let's start with a multiple choice and see if we can apply what we just reviewed. So this one says, based on the standard reduction potentials, what's the value of E standard for a standard cell using silver and chromium? So here's an example of how they would give you reduction potentials. They're always reductions. We know we have to flip one. This is a galvanic cell, so E needs to be a positive value. That means we need to flip one of these before we add them together so we get a positive number. That means we need to flip the second one, and that's it. You don't change the magnitude, you just change the sign. So E cell is the oxidation, which is now positive 0.41, plus the reduction, which we keep the same for silver, 0.80, and we get 1.21 volts, choice B. Very quick, but you have to know how to do that. Some of these incorrect answers are no doubt due to the fact that people can accidentally forget to flip or incorrectly multiply that by 3. You do not do that. You just change the sign before you add them together. Let's try another one. Here's a picture of a better picture of an electrochemical cell. Looks like a Voltaic cell by the fact that they have a standard cell and a 2-beaker system. That's just usually what we see with a Voltaic cell. They note the salt bridge containing spectator ions, and they say, what happens if we put potassium hydroxide in there instead? What will occur? Well, look at the overall reaction, which is given in this question, and let's ask ourselves, what's going to happen if we use potassium hydroxide in this? Well, think about the aqueous ions, and is there any possible reaction that's going to happen when we put potassium hydroxide? They tell us that you're going to precipitate zinc hydroxide, so we need to use that in this information. So if we precipitate zinc hydroxide, that means we are removing the zinc ion. The zinc ion is decreasing. So you're removing zinc ion from this reaction. You don't often use Le Chatelier's principle to explain these questions, but it usually gets you to the right answer. That would indicate that this is going more forward, and I'm going to think that we get more volts out of this. I'm always treating these like free response questions before I even look at the choices. So this is related to the Nernst equation, which has to do with Q. Q for this reaction is simply the zinc ion divided by the silver ion squared. So if I had to use this, I would write out what the reaction quotient is, and if zinc is decreasing, that means Q is getting smaller. Q is decreasing. It decreases. So based on the Nernst equation, E is E standard minus RT over NF ln Q. If Q is getting smaller, that means that this negative term is less significant. So when we subtract something from this E standard, the overall thing actually gets bigger. So E is increasing. You're getting more voltage, increases. Which is exactly what we expect if we thought of this as a Le Chatelet question. Removing zinc ion as a precipitate, more forward reaction, more voltage. So E cell will increase, so it doesn't decrease, it doesn't stay the same. And the reason is not that K ions replace the zinc ions, but instead that zinc decreases and Q decreases as a result. So long way to get to choice A. One more multiple choice. A jeweler wants to plate a specific number of moles of metal on two identical objects in the same amount of time using electrolysis, so non-spontaneous. One with gold, the other with silver. This is called electroplating. This is how we force normally non-favorable overall reactions and get them to occur. It's how we get pure metals onto jewelry. So this is an application of electrochemistry. What do we need to know to determine how much more current is needed for plating some amount of gold versus silver? Well, thinking about dimensional analysis, the moles of the metal could be found by some amount of time times some amount of current, which is a coulomb per time, times Faraday's constant, 1 mole of electron per 96,485 coulombs. And then from that, it's going to be times how many moles of metal, M, we get per how many moles of electrons. So I want to know what's going to change the current. They want the same amount of moles. They want the same amount of seconds. Faraday's constant is the same. So the only thing that's going to affect the current is how many moles of electrons are used to reduce that metal. Even though I'm not solving for anything, I can tell that that's the only thing that's going to have an effect on this, if this is going to be the same. Just using the same dimensional analysis we have in the review on the first page. So it's this difference here, 1 versus 3. So if I look at the choices, the difference in potential, no. If there's 3 times as many moles of electrons needed to reduce gold compared to silver, yep, that's the key. Even though delta G is Morgan negative for the gold reaction, that doesn't affect what's going on here. Same with the molar mass ratio. That might be a true statement, but it doesn't affect the fact that we're looking for moles. This would be needed if I wanted to figure out the difference in mass of each metal, but I don't need that here. I'm just looking at moles. So B is our correct answer. Okay, lastly, let's look at a free response question. There are 2 reactions here. One is as is an overall, followed by a cathode, so a reduction half reaction. And they say the equations above are used in a car battery, a lead storage battery. The first is the overall, the second is the cathode. First up, what's the oxidation number of sulfur in the overall reaction? Let's just review oxidation state rules. So in its compounds, oxygen is usually -2 and H is usually +1, so we figure out the sulfur by knowing that the overall charge is -1. 4 times -2 is a tally of -8. 1 times +1 is a tally of +1, so if this adds up to -1, that must mean my sulfur is +6. So I think I just have to write +6 next to that. And that'll be the same in anything that's a sulfate. Just consider a polyatomic ion as the sulfate ion, and then we know the oxidation state of each element in there. That also tells me that lead is 2+ here. So you can always break apart larger compounds into monoatomic ions and polyatomic ions, which you should know the charge of. You should know that sulfate is SO4 2 minus as an ion. Second half, part B, write the equation for the half reaction that occurs at the anode. In other words, what's the oxidation that occurs? So the overall reaction is up above. We need to come up with what the rest of the reaction is going to look like to give us an anode. Anode means we're going to have some number of electrons as a product. There's 2 electrons in the half reaction for the cathode, so there's going to be 2 electrons produced at the anode, so we could start with that. And then we could just sort of go left to right along the overall reaction and figure out what we need to add to the given half reaction in order to make it balance. There's no Pb solid in the cathode reaction, so it must come from the anode half reaction on the reactant side. There is a PbO2 already. It comes from the cathode, so we can skip that. There's 2 H pluses in the net, but 3 on the reactant side for the cathode, so we need an H plus on the product side so that it cancels with 1 of those 3 to give us a net of 2 H pluses. There's 2 net hydrogen sulfates, but only 1 from the cathode, so we need another hydrogen sulfate in the anode. Now we go to the product side. There's 2 lead sulfates, but only 1 from the cathode, so we're going to add 1 more lead sulfate. And there's 2 waters in the net, and there's already 2 in the cathode, so I think we're done. All we should have to do is check and make sure that this is balanced by itself. 1 hydrogen, 1 hydrogen, 1 sulfate, 1 sulfate, 1 lead, 1 lead. Check the overall charge. The reactants have an overall charge of -1. The products have an overall charge of -1. This is a balanced half reaction, and that's the correct answer. Lastly, after the battery operates for some time, it can be recharged. This is true. This is how you recharge a lead storage battery, by applying a current. How much time is needed to regenerate 100 grams of solid lead by applying 5 amps? This is a dimensional analysis question. So how many seconds are needed to regenerate 100 grams of solid lead? We need to use the current and the mass and other features we know about, constants like the molar mass of lead and Faraday's constant, and get into seconds. So I'm in grams. The first thing I can do is get out of grams by going to the mole. There's 1 mole of lead for every 207.2 grams of lead. Just look it up in your periodic table. So now I'm going to put moles of Pb in the denominator, and I can get into moles of electrons in the numerator. I'll look back up at the half reaction and think about what that half reaction is going to be. Each lead is going to become Pb2 plus, or vice versa. Even though it says lead sulfate, the oxidation state of lead is Pb2 plus. So in my head, I can picture there's 2 moles of electrons for every 1 mole of lead. In fact, we have it right there. They made us write it in the half reaction, so that's why they did that. Then we'll go to Faraday's constant. There's 1 mole of electrons for every 96,485 coulombs. And then we want to know the time given 5 amps. Well, amps are coulombs per second, so write it upside down. There's 1 second for every 5 coulombs. And then if we cancel our units, coulombs cancel with coulombs, mole cancel with mole, moles of lead, grams of lead, and grams of lead, and we're left with just seconds. We simply need to multiply everything out to get the units that we want. And when you do that, you get a very large, let's see, doing it now. It's a very large number of time when you take 96,485 divided by 5 times 2, multiply by 100. I'm not doing it on the screen, I'm just doing it off to the side here on my calculator. When I round to 3 sig figs, I get 18,600 seconds. You get a number more precise than that in your calculator, but since they gave us 3 sig figs, I will do the grader a favor and round to 3 sig figs. Okay, that's a review of electrochemistry and some sample questions that you might see.